Hello, I am Yanming Xiu from Duke University. In this video, I'm going to introduce our work, ViDDAR, Vision Language Model-based Task-Detrimental Content Detection for Augmented Reality. In augmented reality, virtual content are digital elements overlaid onto the real world. They are usually designed to provide users with additional information or enhance experience. However, sometimes the virtual content in AR applications can also be task detrimental to users. This content can be blocking important objects in the real world or manipulating the real-world information. For example, in an AR navigation app, the virtual arrow is telling the user to turn left, but if it's not properly placed, it can obstruct the stop sign in the environment. Neglecting it may cause the user to directly drive into the intersection and lead to potential accident. Similarly, in an AR gardening app, if the plant is placed onto a trash bin, the user may misinterpret the trash bin as a flower pot, and the original functionality of the bin is hindered. There have been some existing methods that can be used to detect detrimental content in AR, such as applying full reference image quality assessment methods. However, they usually rely on local features. This limits their ability to understand environmental information and simulate human perception. Other methods are usually based on machine learning methods, using object detection models or optical character recognition models to understand scene information and evaluate the virtual content. But these methods still remain at a low level of comprehension and find it hard to understand the environmental context information. Recently, vision language models, which integrate both visual and textual understanding for cognitive tasks, such as image captioning, reasoning, and visual question answering. Vision language models offer a potential solution to detect task detrimental content because it is effective at context-aware analysis. More importantly, in another work of ours, we discovered that VLMs are also highly sensitive to the virtual content in AR. With such background, in this work we have the following motivations. Firstly, we aim to clearly define common types of task detrimental content in AR. After establishing these definitions, our goal is to develop a systematic and scalable solution for detecting such content. Specifically, we seek to leverage VLM's contextual awareness to enhance automated AR content analysis. The basic assumption for our system is that it should work as an independent security layer, which means it has only access to the camera feed and the user's view, without any direct access to the internal data of AR applications. The system input is the raw image and AR image. With such assumption, we first define the obstruction attack, where virtual content blocks key real-world objects or information. In the raw image IR, there are some key objects. Each key object has a pixel mask. The type of key objects are not predefined and depends on environmental context information. Meanwhile, in the AR image, the combination of virtual content has an overall mask. We can compare the virtual content mask and the key object masks. If certain percentage of any key object is obstructed, we consider that in the AR scenario there is an obstruction attack. Another kind of more complex attack is information manipulation attack. The real-world element is not directly blocked, and instead manipulated in a more subtle way. Similar to obstruction attack, there is a set of real objects in the raw image, and all of the virtual content is still denoted as C. For each real object and virtual content combination, 3 Boolean factors are aligned. Alignment precision determines whether the real object and the virtual content are spatially aligned. A bad alignment makes the virtual content easily recognizable and difficult to manipulate real-world information. Style similarity determines whether the real object and the virtual content share a similar visual style, such as color and texture. Low style similarity makes virtual content hard to blend into the scene. Information misrepresentation decides whether the virtual content manipulates scene information. If all these 3 booleans are true, we define there is an information manipulation attack. After defining these attacks, we designed our ViDDAR system to detect these attacks. This diagram shows the system architecture we designed for ViDDAR to detect obstruction attacks. It mainly consists of three components: a user AR device, an edge server, and a cloud server. The AR device continuously captures raw images and overlays virtual content onto them. It transmits both the raw image and the AR image to the edge server and receives obstruction detection results. The edge server receives the image pair from the AR device. The raw image is sent to the cloud server with a text prompt to detect the key objects. This process is managed by a prompt controller to minimize resource usage. To manage the detected objects, we introduce a key object list, enabling ViDDAR to remember these objects. Simultaneously, each raw image and its corresponding key object name list are passed to a multi-model object detection module, followed by a segmentation module to predict the key object masks. Finally, these masks are compared with virtual content masks at the pixel level and output the attack prediction. The cloud server hosts a VLM, which processes the encoded raw image, identifies the key object within it, and sends the name of the identified object back to the edge server. And this diagram shows the system architecture we designed for ViDDAR to detect information manipulation attacks. It also consists of three parts. Similar to ViDDAR for obstruction detection, the AR device here also continuously sends both raw image and AR image to edge server for processing, receiving information manipulation detection results. The edge server sends both the received raw image and AR image to the cloud server. Given that the cloud server analyzes multiple factors, the VLM's output can be complex. Thus, a post-processing module is implemented on the edge server to interpret the VLM's output and provide a binary true or false decision. And still, the cloud server employs a VLM to detect information manipulation attacks. Here's the system evaluation part. To start with, we evaluate ViDDAR's performance in detecting obstruction attacks. We collected a dataset with 306 raw image and AR image pairs. We tested two VLMs, GPT-4o and Lava Next 8B. We used the grounding dyno as the multi-model object detection model and segment anything as the segmentation module. We also designed the prompt for ViDDAR to detect obstruction attacks, using techniques such as role assignment and few-shot prompting. And here's the evaluation result. ViDDAR can achieve higher than 92% obstruction detection accuracy. In the baselines, end-to-end, under-detailed, and greedy are different ways of prompting VLMs. Each exhibits some performance drop. Saliency map and canny edge are classic computer vision-based methods. Then we evaluate ViDDAR for information manipulation detection. We collected a dataset with 114 raw image and AR image pairs in 10 scenarios. For each image pair, we manually labeled its labels of the three Boolean factors and overall information manipulation status. We also designed the prompt for VLMs using a chain of thought to detect information manipulation. Here's the evaluation result. When using GPT-4o as the VLM, ViDDAR achieved higher than 82% obstruction detection accuracy. When using Lava as the VLM, the detection accuracy dropped significantly, probably due to the small model size. To validate the datasets label aligned with human perception, we conducted a user study and recruited 20 participants. They are given some example images in the datasets and need to provide their feedback to some statements related to the image labels. The feedback is quantified using a 5-point Likert scale. The user study results shows that all label categories received an average score higher than 4, which means the participants generally agree with the dataset's labels. Lastly, we tested ViDDAR with real-time application scenarios. We implemented the two applications for Android phones with Unity. We measured the detection latency by recording the screen and checking the time between an attack happens to the detection information pops up. We also tested in two different network settings. Results shows that ViDDAR can achieve a latency as low as 500 milliseconds for obstruction detection in a one-hop network setting, allowing for rapid detection without obvious delays. Information manipulation content detection takes considerably longer, but it remains suitable for applications where periodic evaluations of information manipulation are sufficient. In conclusion, we have formally defined two types of task-detrimental content in AR. To detect these attacks, we propose ViDDAR, the first system to leverage VLMs for detecting task-detrimental virtual content in AR scenes. We tested ViDDAR on datasets and real-world application, and ViDDAR achieves a balance between detection accuracy and latency. The dataset we developed for this work is publicly available at GitHub. Our ongoing work includes deploying ViDDAR to head-mounted AR devices. We have a demo that integrates ViDDAR to MetaQuest 3 available at IEEE VR demo session. We are also working on defining and detecting some more kind of subtle and malicious attacks in AR. A quick example we are working on is digit manipulation attack. In this speed limit sign, we can manipulate the number 3 and make it look like an 8 to provide users with manipulated information. Finally, we would like to express our sincere thanks to Ajay, Yunye, and Junfeng for their help on this work. That would be all of my presentation. Thank you all.